All right, so now we have some interesting stuff to introduce. So if we have some finite set, and we have some subsets, so this is something like clubs in our even town and our odd town, right? So we have first subset, I don't know, second subset, and probably the third subset. Right, so we refer to them as points and blocks respectively. Now we can construct, if we have points and blocks, then we have construct so-called incidence matrix and adjacency matrix as follows. Right, so I'm going to give you an example. Let's say we have 5 points and say 3 blocks. This is going to be the first block. This is the second block. I don't know. This is going to be the third block. So first, second, third. And the points are going to be like A, B, C, D, and E. And so then we construct a matrix whose rows are indexed A, B, C, D, E, and whose columns are indexed by blocks 1, 2, and 3. So, okay, so then we're going to look at, say, the first column. So the first column is the first block. It contains elements A, B, and C. So I'm going to write 1 for A, 1 for B, 1 for C, and zeros for D and D. The second block contains elements C, D, and E. So C1, D1, E1, and zeros for A and B. And the third block contains D and E. So 1 for D, 1 for E, and zeros here. Right, so this is the incidence matrix M. All right, so then we have the adjacency matrix. And the adjacency matrix is indexed by both rows and columns correspond to points. All right, so if we have, I don't know, something like this, 1, 2, 3, say 4 points, A, B, C, and D. And then let's say we have, this is the first block, this is the second block, and this is the third block. Then the adjacency matrix is indexed by A, B, C, and D, A, B, C, and D, right? So A belongs to, how many blocks does A belong to? 2, right? So A and B together belong to just 2 blocks, right? So A and B belong to 2 blocks together, so 2. So A and C, we look now at A and C. So A and C belong to the first block together, so 1 here. So A and D do not belong to the same block, so 0 here. Okay, so B and B. So B belongs to all the 3 blocks. So 3 here. B and C belong together to just 1 block. B and C. Well, and so on, right? So this is how the adjacency matrix is constructed. Well, but then if you think about it, then the adjacency matrix is just the incidence matrix times the incidence matrix transposed. Right? So why is this true? Is because so what are entries of the matrix M times M transposed? So these are entries of this matrix are rows of matrix M times columns of matrix M transposed, which are again rows of matrix M, right? So in other words, these are dot products of rows of matrix M with themselves. And rows of matrix M are zeros and ones. Right? So there are zeros and ones. And ones are there at positions of blocks that the given element belong to. So if you take this dot product, then like in this example, so we have 6 blocks, and the given element belong. So the element I, sorry, maybe I just did the same. So maybe it's not a good idea. So forget about this. So maybe row I and another row J. So say 0, 0, going to be 1, 1, 1, 1. Right? So it means that block I belongs to, sorry, element I belongs to blocks 3 and 4, and element J belongs to blocks 3, 4, 5, and 6. Right? But then if you take the dot product, only ones at positions, only positions where we have ones in both ith row and jth row are going to persist. And those precisely mean blocks that contain both I and j, right? So it means that kind of by construction, elements of the matrix M times and M transposed, they count the number of blocks that both I and j are in. So which is precisely the adjacency matrix, right? So the adjacency matrix is M times M transpose. Okay, but then you can consider the dual construction, so which is called the block intersection matrix, right? So its entries are indexed by blocks, and the entry is the corresponding to 2 blocks is just the size of an intersection, is how many points are in the intersection of blocks B and C. And of course, this block intersection matrix X is going to be the opposite, right? It's going to be M transposed times M by exactly the same logic. So A is M times M transposed, and N is M transposed times M. All right, and just a little remark, sometimes the notion of block is kind of is not explicitly used, but it is always somehow there, so you can always figure it out. If, say, you have a graph theory problem, then your graph can be considered as blocks, where blocks are just edges of the graph. Or if you have clubs in odd town and even towns, then those clubs are actually just blocks.